Welcome, everyone. This talk is now going to be on docs, CI tests, error messages, and interfaces in Julia SciML, right? So, what do I mean by this? So, what I really mean by this is that the TLDR of this talk is that SciML has formalized many processes, right? We had an inflection point in 2022, and in the State of SciML talk, I kind of described a little bit about that inflection point where, we changed from being Julia DiffyQ to SciML, but then a lot of other things had happened at that point too, right? We had a lot of companies that grew up. Pumas AI was, founded in 2019, and then by 2020, it was being used for the Moderna vaccine, and then beyond that, it just it started growing fast. With Julia Hub, we started growing, and we started using things in a lot of safety critical applications. And we had the whole MIT Julia Lab grow up, and the number of contributors grew for other reasons. And so it couldn't just be a small organization anymore, where it's like, oh, we run a few tests, and then after you run your test, you let the package go and see if it works out, right? It's like no. So it had to become a whole enterprise of just how do you make sure the entire thing stays maintained, right? And so because of this, we needed all benchmarking. We couldn't just say, hey, let's benchmark it and then post your benchmark results. We need to start to be able to say the benchmarks need to be fully reproducible, so that way we can all update the same benchmarks, and we can keep a timeline of all how performance changes. So that way, if someone makes a commit that makes something code go slower, we know exactly what code did that, and that was either a choice we made because it's like a correctness improvement, or it's something that we need to revert, right? And so we need to make it so that way, did you break anything is not just a small unit test. It's did you break anything here? Did you break anything downstream? Did you make anything go slower? Did you make it so that way putting code onto robots, embedded code onto FPGAs, did you make that harder, right? Every single detail like that, we need to be able to understand from every single change that any contributor says, oh, hey, here's a PR that fixes a typo, right? We need to know all that information, because it's not, because Julia and SciML is being used in so many places that we have to consider all of this now. And we need to make it so that way a contributor who knows nothing about most of those applications, their code is being worked and tested like that, right? But not only that, but we need to make sure that the documentation then works as a system that is not just on a website, the standard documenter, but how do we make it so that way the documentations all talk to each other, so that way if you work with the differential equation solvers, and then we say, hey, we're referencing something over in the symbolic library, how do you make it so that way you have these cross references between a few hundred libraries? You have to be able to build them all together, right? And you need to have error messages that target non-experts, and you need to have your interfaces be strictly defined. And I think that last piece is a huge piece that a lot of people might not have even known that we've done, right? So in 2016 or so, we wrote some blog posts about how, hey, look, in the OD solvers, you can put anything in there, and any number tends to work, and whoa, you could just find out whether code works just by letting generic interfaces work, right? And there's still a lot of generic duck typing that we do. But now all of our interfaces are strictly defined and tested, and there's certain guarantees that we are able to put on code if it satisfies the interfaces, right? So we've really built up our own interface system throughout SciML, and I'll be talking a lot about the formalization of the interfaces. And so there's a lot of stuff that we used to say back in 2016 or 2018 or even 2020, which is just, no longer true about the organization. Now the organization, it's run as a machine with, literally machines checking if you don't break any interface assumptions and all that, right? So I want to talk about how we've done all this, because a lot of other organizations can adopt our approaches, and so we want to share what are the things that we're doing and what are things that every other Julia code should be doing, right? And we kind of want to scold you for not doing some of these. There's a complimentary talk. There's a talk that I gave back in about 7 months ago in Erlangen on maintaining large-scale Julia ecosystems. It is not the same talk as this at all. It instead talks about 7 axioms for maintaining an extremely large-scale organization, and the high-level points to think about. I'll call that a complimentary talk that you should go check out if you're interested in this kind of content. So again, I just gave the State of SciML organization talk, which explained what is a SciML organization. But the key thing here that I want to highlight is that the organization is huge. There's hundreds of unique contributors every single month. And so what do we do in order to make sure that the code that comes out of here is reliable and it works everywhere, and And again, since we're talking about hundreds of contributors, we literally do, the people who do the package management statistics, right? They told me that before they got up to that state of Julia talk, that they're like, yeah, we calculated out, how many releases are being done, but we realized that the SciML organization is making 3 package releases a day on average. Right. So there's so much code going out that there's packages releases going every single day. So how do you make sure that when that's happening, that every single new patch, everything's working, right? So what are the rules, right? So how do we even make this work, right? So one of the key things that's really happened is that we've had this SciML style guide, right? And so we say the SciML style, it's the stylish guide for stylish Julia programmers, right? What it's all about is this is exactly how you should program. And there is a section that is about like, oh, here's how you format code. Like when you do a doc string, your doc string should start with, if it's a type, then this is what a canonical doc string looks like. And so that way when people give a pull request, we don't tell them like, oh, I don't have to go in there and say, oh, here's how I would do this. It's like, read the SciML style guide and come back when it's matching the style guide, right? So while there is a section on syntactic formatting, I think the thing that's more important about the SciML style guide, which if you haven't seen it before, would be very useful, is that the majority of it is dedicated to higher level style choices about how to code effectively for performance and maintainability. And so it's all about having these axioms. And I just want to, what do I mean by that? Here's one of these axioms that we put there, right? Always default to constructs with initialized data, which means, there are constructs that you can do where you say, I create a vector of undef, or I use similar. But if you use those operations and you have undefined memory, and there are certain bugs that could happen down the stream that are hard to find. So therefore, always default to using things that are writing actually zeroing the memory, except if you can prove that you have a performance benefit for that. And if you have a proof that you have a performance benefit from that, you better also give me a CI test that says that it's still faster. So that way, if it's not faster in a Julia version, we can also make sure that we initialize the data at that point. Right. So this is one of these axioms where you just say, if anyone ends up using similar in the code, we say, no, it shouldn't be similar. It should be 0. You should zero that memory, unless you can prove to me that you actually are faster with the uninitialized memory, right? So this is one of these high-level points, but actually the SciML style guide has a whole lot of these points, right? Things like avoid any operation that is called unsafe, avoid eval, closures should be avoided. Why should closures be avoided? Well, because there's a boxing rule with that can happen within, So some of these are related to the way that Julia optimizes code and the way that the garbage collector works, and we say, these are certain styles that we use, or these are certain styles that we avoid, because we know that this gives you code that is better for static compilation, code that is better for compiling to WASM, code that is better for compiling to GPUs. All of these things need to be true about our code, so we need to make sure you have a style guide on the code that makes it so that way it's not just, oh, hey, it works for my computer. It's like, no, it's got to work on Windows. It's got to work on Windows 32-bit, even if you don't use it. It's got to work on ARM. It's got to work on GPUs. And so this is a style guide where if you follow the SciML style, then things will work pretty well universally. But we then have to make sure we write it down so that we share this with everyone. And so these are the rules. And if you want to know each of these rules in detail, I'd be happy to chat about any of them. They all have an explanation as to why it's there. Sometimes it's limitations of LLVM. Sometimes it's limitations of Julia's optimizing passes. And sometimes they're fundamental limitations in computation. So we established a whole bunch of rules that we throw onto everybody. Then we also have COLPRAC, right? So we have this library called the Contributor's Guide on Collaborative Practices for Community Packages, which basically says all the things that you should do when you're contributing to a SciML organization package. Now, there's one thing I wanted to highlight in this list, which is the continuous release process, right? So COLPRAC, as what we do as an organization, and the way that we found to be able to make the scalability work, is that we establish a continuous release workflow for the organization, which means after a pull request, your code should be good enough that we should be able to release with it. And this is one of the reasons why we have so many releases, right? Because if we take in a new feature, well, we should be able to release it and give you that new feature. Nobody should be checking out the master version of our package for a month, because then we actually have to do something with you, right? So I remember like early in 2018, we'd say, oh, hey, check out master. And if you want to use this new feature, and then what I actually would find is that that user was still on the master branch 2 years later. And they're like, oh, I found a bug, I found a bug. And it's like, how'd you find that bug? It's not even released code yet. Well, you told me to go on master 2 years ago. They're like, no. Only use released versions of packages. We will release features immediately when they are ready. Which means, but we always release from main, which means that things can only merge if they are release ready. And so this is the continuous release process. When we merge PRs, we do a release. Merge a PR, do a release. And it has many advantages because you basically know that everything on main is fresh. If you merge a PR, what are all the new features in that new release? It's only the things in the PR you just merged. Like everything is much more local, and then users are never told to go off main. And we also have all these checkpoints as to every single version. So then everyone, if there is something that is a regression that shows up, we can know exactly what version is involved there. And the thing is then that the only way to get things done then is to be able to take really big idea PRs and break them into small little chunks. So that way you're chunking out one little feature at a time, which makes it a lot easier to be able to get things maintained because you're no longer saying like, oh, we're going to completely change this entire package in one pull request. No, we're going to do small changes one at a time. And if you can't do small changes, most likely the reason why you can't do small changes is because you're completely breaking interfaces, and we need to talk about this, right? So it really discourages people from doing things that just completely break anything, and that's really what we're looking for when we're going for maintainability. So those are the rules that we've established, and it's really helped us a lot. And the next thing is all about documentation. So what do we do about the docs? So the real question is, how do we make a few hundred packages look like they're actually one unified set, right? The way that we've done this is that in 2023, we released this global documentation where the documentation of all the packages are put together into a single form, so that way they have cross references within the search bars. So if you're using, you're using differential equations.jl and you see a part of the tutorial that is telling you, hey, use symbolics for sparsity detection, you will then get a reference over to symbolics where it will tell you this is where this function is defined, right? Because again, there's a whole ecosystem, right? You almost can't even think about a package on its own, because when you use the differential equation solver, you're also using linear solvers, you're using automatic differentiation tools, and so we had to really bring all the documentation together into one system in order to make that make sense. And then we had to establish a lot of core documentation principles. Since I'll be running low on time, I won't go into all of them. But the key thing, though, is that we always are putting a getting started tutorial on the top. And every single Julia package should do that. The first thing that you click on should be a getting started tutorial. And why is that? Well, what we found through the package analytics is that 90% of people will only look at your first tutorial. They will skip all of your, it doesn't even matter where in the manual things are, you can put all your manual pages on top. They will go to your first tutorial. 90% of people will read that first tutorial, and that will be what they think of as your entire package. I now have, I have the Google Analytics for over 100 Julia packages here, and I can tell you that literally every single package, doesn't matter what order we had the documentation in, everyone already did that. So we moved that to be the first link on every single documentation, and we made sure that every single core functionality that we want people to use and everything that we want people to know about this package better be in that first tutorial. Everything else is useful other pages, right? But 90% of people will only ever click on that first tutorial. And I know I'm looking at people in the audience who are laughing. You're saying, oh, I do that. Yeah, you all do that. So the analytics don't lie, right? So there's other things to do about, I guess one other point to make in the documentation is that we've really separated out the idea of tutorials versus examples, right? So tutorials are about showing a functionality of the package. And the point is that you want to make the example as small as possible. So, every tutorial has the smallest differential equation definition possible. It tries to be like 5 lines of code. And then you say, oh, you want to use ensemble threads. We show you how features work, right? But then the other thing that happens is someone just goes, well, in all of your tutorials, you use ensemble threads, but then the threading's not actually faster. And we're like, yeah, because it's only like one ODE, and like you need a big enough model. Da, 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 da. So this is where you have examples, right? So tutorials show you how to use features, so that way, it's a very nice, succinct code that shows you how to do something. And then your examples show you like, oh, here's a gigantic model, and we do multi-threading on it, and so therefore it's faster, right? And so if you separate those two ideas, then it becomes much easier to be able to say, hey, yes, we have the gigantic examples, but the gigantic example is not infiltrating, I don't have to have, all this MPI code around just to be able to show you, yes, here's how distributed coding works, right? So separating those two has really helped out a lot of our documentation. And here's just a few examples. So so the difference between a tutorial and an example is like, we have a tutorial on the left where you say, hey, we use the Lorenz equation. Like we use the Lock-Voltaire equation, the Lorenz equation almost every single time. Why? Because there are 3 ODEs and everyone already knows them. That makes it easy to be able to talk about things like, okay, how do you set tolerances? I don't need to have a 500-page ODE definition to be able to tell you how to set tolerances, right? But, you want to go see some other examples? You want to start talking about deeper features and sparsity detection? Yeah, okay, we have another page that goes into those and shows you how to make use of those deeper features, and we separate those two to make it so that way it's much more legible, right? And so you can see that, and then some of the examples go into things like, oh, how to use the symplectic integrators. Yeah, there's also a tutorial page that covers the same topic, but the examples show you how to do this in physics. It shows how to do this in biology. It shows how, and so like you can really hit all those terms that people are looking for in terms of specific parts. And some plan changes that we want to do is that there are some nicer ways we could show these examples. Instead of having them all in the sidebar, we could have nice pictures for these. And it turns out that there is this demo cars.jl, which Morten had been building within Documenter, so that way you can list out all your examples where you say, here's a picture representative of it, like Kepler problem. You show a picture of orbits, and you have a nice description under it, and you can have all these cards for it. We don't have this integrated into our documentations yet, but this is what we plan to be doing with our examples. Because right now there's just a sidebar that says like examples, and just has them all listed out. But we plan to be reformatting that in the very near future. So I do want to say that, writing a documentation is basically the same as writing a murder mystery TV show, right? You think about like a CSI TV show, you want to start with a cold open that sets the stage, and it's like, oh, here's everything that's cool. This is the getting started page, right? You just say, here's everything that's cool in the package. Put the sunglasses on. Yeah, the opening to CSI. But after you do that cold open, you play the theme song, right? Which is just, showing a bunch of examples really quickly. Like you could do this, you could do this, you could do this, you could do this, you can do this. If you think about like the theme song of a show, it just shows you very small clips of all the things you can do. When you finally get into the meat of the show, you write these big tutorials that is like, okay, here's one story, here's one story, here's one story. And then you have the manual after all of that, right? Like, the page of just all the doc strings, that goes after all of that because most people don't want to read that. It's like most people just don't want to read doc string after doc string after doc string. You should have it, but most of the things should be contextualized as a story that is then walking people through why these features are there, right? So keep up with time. I'm going to get to the testing part. So here's the thing, right? So we have hundreds of repos, and one of the things that happened in the last year was, for example, the CodeCov organization changed their policies. So that way, if you had 20 pull requests or 20 jobs that happened within an hour, they would throttle you. And since we have a pull request open probably about every 5 minutes, we got and that opens up 10 or 20 jobs itself. We were basically throttled into the point where CodeCov is no longer usable when they made that change. And so we had to go to every single library and update the CI process. That meant that it took about a few hundred PRs just to be able to update our CI because one system changed. So what we've done instead is we said, okay, let's centralize our controls. So what we can do instead is you can have a repo that is called the .github repo within your organization, and you can put your standard CI scripts there. And what it ends up looking like, I guess we don't have a picture of that, but what it ends up looking like is you just say, my test.yaml file for my CI, its definition is go look at the .github repo. And so we basically have now most of the organization's CI scripts just say go look up at this one other repo. And so we can, in one space, we can change the way the CI works for all of the different packages in the organization at once. And the thing that is nice about that is it means that every single package is being tested and being, having the same test setup and everything in the same way. And so, for example, when the new LTS changes to Julia version 1.10, we can in one part of the organization make a change, and now all of our packages update the LTS. The latest or the last release that we test on will be 1.10, right? And so if you are having issues trying to maintain large numbers of packages, I would check out how this .github was set up by Anant, and this is something that a lot of other organizations should use as well, because if you start to be able to say, oh, every single package has its own CI scripts, then you also have the problem of some of them will test on Linux, some of them will test 32-bit, but they won't all be testing the same thing, right? And you really want to make sure that gets unified. Another big thing that we've done is a lot of environment-based test parallelism, right? So within the CI test, we specified that we're going to run the test over a bunch of what's known as groups, right? That sets an environment variable that we then read within the CI script. And so then within the CI script, it just checks, is the environment variable group equal to interface 1, equal to interface 2? And what this means is that we then just spawn the test strip with these different environment variables, and it'll run then on that subset of tests. So for ordinary diffie-q, I think it has like 20 different test sets. And so when someone creates a pull request, it will automatically spawn 20 different CI jobs, each of them with a different environment variable, and thus each of them only running a subset of the tests, which means that each of these jobs that are created are all in parallel running one small set of the test suite. So the ordinary diffie-q tests take about 6 to 7 hours to run in total, but you don't actually see that because each subset of it's like 15, 20 minutes. It's just running on a whole bunch of different machines at the same time, and it's very easy to set up with just using environment variables. And we also have the special build kite, which is what we use for any large-scale GPU jobs or for any gigantic tutorials like diffie-q flux. Takes about 3 hours because it wants to show you how to train neural networks and neural ODEs. And so therefore, we have a special CI machine that's set up that just is continually using its GPU to be able to retrain the same neural networks over and over and over, because it's also a good test for did anything change or fail in the training. Well, we can check whether the documentation build failed. We also do downstream tests for everything. So I would encourage that everyone steals our downstream.yaml. It's a really nice file. If this file exists within your repo, then what will happen is that anytime anyone opens up a pull request, it will also do testing of your downstream users. So why is that the case? Well, because, for example, in SciML base, that defines how ODE problem is defined, which then every solver from ordinary diffie-q to stundials, all these solvers use that same type definition, right? So if we change that type definition, we don't want to just do my test pass, but did I break anything in any solver, right? You use this, you use this, you use this, you use this. And what the downstream.yaml lets you do is it lets you be able to say, these are all the packages that I know are closely related to this one. Let's make sure that none of them break from your PR. And that gives us a stronger definition of breakage, right? It's not just, did my test break? But it's also, did anyone who uses my package, did their test break as well? And if you start to put those tests on, people are much more reluctant to make a breaking change, which is a good thing. Because then you say, okay, if you do want to do breakage, then we will do the proper response of we will have to bump the major version. But if you bump the major version, well, it is now for you, the person who made this PR, who broke the thing downstream, you have to go make a PR to the downstream package saying, I'm sorry I broke something. Here's the fix for the change that I just made as well. This is one of the policies that we've implemented, and that makes it so that way, if breakages actually happen, the packages that are relying on that piece of code, they should get a pull request from us, They shouldn't find out 1 month from now that, hey, something broke. I need to go find out what these SciML guys did. Like, you should actually get a pull request from us that says, we changed this interface. We bumped the version. You got a compat thing that you have to change. Here's the fix for you, right? And we can find out when we have to do that using the downstream testing. So every Julia repo should have the downstream testing put on it. I will die on that hill. We also have automatic formatter suggestions in the in CI. So I mentioned that with the SciML style, we tell you how your code should look. Well, also GitHub will then show you that, hey, your code doesn't actually match the style. Like here's the line length limit. So here's a suggestion how you should fix your code. And so you've been rolling out this automatic formatter. Again, you can steal any of these scripts from us, and if that you want. There's also compat helper and tagbot, and what these do is if we do make a change that is breaking, we will bump the major version, and then anytime that a major version is bumped, it will open up a pull request on every single repo that is one of these that is depending on it, and then we'll have a pull request that says, hey, you need to be able to test and make sure that you're allowed to use this new version, right? And so all of this is done fully automatically. So error messages. So in 2022, our error messages were downright awful. We basically just relied on whatever error message was thrown within the code, and that did not necessarily get you great error messages. What we've done now is we've moved all the error messages up to the SciML base layer, so that way very high in the interface, it then is checking if these properties that we know have to be true are true, and then we throw a contextualized error message in order to be able to do that. Some of them go pretty deep. So here, for example, it's checking whether the number of arguments in your function are matching the requirements for the ODE solver, and so it will check, is there any dispatch that does not match this argument, and we then throw a very contextualized error message that says, we know that a lot of people in MATLAB and SciPy do this thing where they just write out all of their parameters, but our syntax is not like that. Look at this thing. Go look at our documentation on that, right? So because we're able to know from years and years of answering people's questions that you don't just have an error that's just like, oh, hey, I used too many arguments. Almost every single person that was putting too many arguments in the ODE solver is because that's how you actually do things in SciPy. So we should tell them, like, I understand you come from SciPy. I understand you write code like this. But here's, this style in SciPy is equal to this thing in Julia, right? Because most of the time, these are the issues that people have. It's not just like a type, okay, there's a lot of typo things as well. But a lot of times it's this translational thing. And that's something that standard error messages will not get for you. How does the thing that I was doing before, how do I translate it in my mind? But also we have a lot of interface tests in here. So, for example, we say, technically the ODE solver actually works. If you start with float 32 numbers and you change your output to float 64 accidentally, the ODE solver actually works. But in 2023, we put an error message on that to be able to say, you now have a type mismatch because almost certainly you did not do this on purpose, right? And you can see this is an example where you're multiplying a value by 1.3. 1.3 is a double float 64, whereas your values before were float 32. And we say, after the first step of our ODE, your type has changed. You can actually disable this error message, but you probably don't want to be doing that, right? And so by doing all these high-level interface pieces, we can really make sure that people write code that is correct. And then the next thing is interfaces, right? So we have, I'm going to be running out of time, but we've basically taken the time to be able to define every single interface that we have. So, we basically be able to say, if you want your number type to work with SciML, your number type has to satisfy that 1 unit of t times, 1 of t equals da. Like we've gone and written down all of these things need to be true, and we're adding tests to make sure that, your properties of your types actually work out before we even try to hit the solver. And if it doesn't, then we tell you that you're not matching the interface. And so we have all sorts of interfaces: common solve, SciML base, SciML structures, which is an interface on how parameter types should work, array interface, which tells you how arrays should be working, and there's just interface after interface after interface after interface. I will not have enough time for that. But we no longer are in this world of just saying, just throw something into the package and see if it works. No. We have all these interfaces that tell you exactly when things are true and false, and we have functions to be able to check all of that. And you should be defining your functions to that, otherwise we are throwing errors. Lastly, we have continuous benchmarking with SciML benchmarks, which is a fully reproducible benchmark system. If you put a script onto the system, it will automatically run on a computer that we have at MIT, and it'll generate all the plots. And we use that then to be able to say nobody runs a benchmark on their own machines. And contrary to popular belief, we do lose some benchmarks, but the reason why we don't lose them is very often is because with a moment we see that we're not at the fastest at something, we tend to get all of our work on to make sure that we're going to be fastest there. Which means give us more benchmarks where we're not the fastest, because that's where we find all of our good work. And over time, we plan to be rolling out per repo performance regression benchmarks. This is already on lux.jl. We plan to be doing that in the near future everywhere. So thank you, everyone. I'm way out of time, but these are all processes which I believe every Julie package and organization should adopt. Thank you.